So thanks for the invitation. No, shame we can't all be in Vienna in person, but such is life in 2021. Glad to have a chance to be here on Zoom today and to tell you about a story that I've been exploring for the past 5 years with a range of collaborators, and we continue to discover new stuff. And today, I'll be telling you about sort of the greatest hits from these papers on this opening slide, and which all sort of fall under this general theme of what I call Fracton dynamics. So just to set the stage, let me say that, look, this is fundamentally a story about ergodicity breaking. So at this conference, I don't need to explain why non-equilibrium systems are interesting, and maybe the most interesting way to be non-equilibrium is to be non-ergodic. But then the question arises, how can we break ergodicity? And historically, there's two ways that we knew of to do it. The first, of course, is integrability, and that involves having infinitely many explicit conservation laws. And the other way that this has been very topical in the past couple of decades is many-body localization. And many-body localization actually also involves an infinite number of conservation laws. Just this time, they're emergent conservation laws. They're the local integrals of motion, or LBITs, of the problem. So there's two ways we know of to break ergodicity, integrability and localization, and they both involve infinitely many conservation laws. Now, can you do it without infinitely many conservation laws? One key takeaway from the study of Fracton dynamics is, in fact, there is a way to robustly break ergodicity with just finitely many conservation laws. In fact, just two will suffice. So you can get away with just two conservation laws if you pick the right two. And the key insight as to how to do this came about from the study of something called fractons. So the way I'll structure the talk is as follows. I'll start with a brief introduction to fractons. Then I'll explain how you can use principles derived from the study of fractons to robustly break ergodicity. Then I'll move on to discuss something I call Fracton hydrodynamics and various intricacies of Fracton hydrodynamics before finally concluding and giving some outlook. What are fractons? So I should say my discussion here is going to be extremely cursory. If you want more detail, you should go read the review paper I wrote on the topic with Mike Remley. But the bottom line is fractons are a new sort of phase of quantum matter. And they were originally discovered in 3 spatial dimensions in the context of exactly solvable lattice models, although now we do understand how to get much of the essential physics in lower dimensions as well, but originally they were discovered in 3 space dimensions. And their defining property is that the elementary excitations exhibit fractionalized mobility. That is, an individual excitation either cannot move, or it can only move in certain directions but not in others, whereas conglomerates of multiple excitations can move freely. And the fact that you have this fractionalized mobility, I first discovered fractons and realized, I realized that this sort of fractionalized mobility existed in fractons 5 years ago, and got very excited because I figured that this gave us a new way to evade equilibration, and realize new sorts of non-equilibrium phases of matter, and that I've been exploring ever since. And indeed, there's new possibilities that open up. And some of the new possibilities that open up, in fact, most of them can even exist without microscopic fractons. So you discover these new possibilities by starting to think of these exotic quantum phases of matter, and then you discover that much of the physics can also be realized in much more prosaic settings, including the sort of ultra-cold atom experiments that Monica gave a beautiful talk on immediately before mine. So now let's talk about evading equilibration with fractons. Maybe the key thing to take away is where does this restricted mobility come from? So it's there in the exactly solvable lattice models, and you can see it from exact solution to the lattice models. But the lattice models are kind of baroque, and so I don't want to go into the lattice models right now. Instead, what I want to tell you is this great insight of my brilliant former postdoc, Michael Pertko, which is that the restricted mobility actually comes from conservation laws on multiple moments of charge. So we're used to thinking of charge conservation, but Fracton models, in addition to charge conservation, they also have, let's say, dipole conservation, or conservation on some sort of higher multiple moments of charge. And the exactly solvable lattice models, well, these conservation laws are Z2. So a lattice model might typically have Z2 charge conservation and Z2 dipole conservation. Yeah. And those exactly solvable lattice models, actually, they don't do what I'm looking for. So you can go solve them, and you find they have glossy dynamics. The time scale on which they equilibrate is very long. But at the end of the day, they do respect ergodicity. There's just a long time scale. Yeah? And the reason they respect ergodicity is really that the Z2 constraints are too weak. And if we really want to get like truly new physics, we want to promote from Z2 conservation laws to U1 conservation laws. And the rest of this talk is really going to be about what you get when you promote from Z2 conservation laws to U1 conservation laws. Yeah. So what we'd like to consider the sort of the minimal, you can put constraint, like you can have various U1 multiple conservation laws, but the very minimal realization to consider is you have conservation of charge, like honest U1 charge, and you have conservation of U1 dipole moment, yeah, which might look very artificial, but it's realized both in various Fracton phases and in ultra-cold atom realizations like what Monica was just telling us about. Okay, so we want to consider quantum dynamics with charge and dipole conservation. And that's, so the only constraints we want to put on are charge conservation, dipole conservation, and spatial locality. Yeah. And we could do this in arbitrary dimensions, but it's instructive to start in one dimension for starters. Everything should be made as simple as possible. So let's start in one dimension, and maybe let's even consider a spin chain in one dimension. And the conserved charge can just be the z component of the spin, defined in the obvious way. And the conserved dipole moment can be the position-weighted z component of spin. Yeah. And now we want to consider quantum dynamics, which conserves charge, conserves dipole moment, and also has spatial locality built into it. So what that means is that charges are immobile. A single charge cannot move because that changes the dipole moment. But a single dipole, a plus charge and a minus charge close together, that can move freely without changing either charge or dipole. And single charges can move. So you can think of this either as a charge hops right and emits a dipole to the left, or a charge hops left and emits a dipole to the right. And either of these processes preserves dipole moment. And now we want to consider minimally structured quantum dynamics, which conserves charge, conserves dipole, and has spatial locality. So the simplest way to implement this is in the context of a circuit model. So you can build a quantum circuit where the quantum dynamics is generated by unitary gates. So that builds in locality from the get-go. You have some range of gates that determines the range in which things accrue. And each of the gates is constrained to respect charge and dipole moment. And then you build up your circuit in this way. And this is a model of sort of minimally structured quantum dynamics, which has charge conservation, dipole conservation, spatial locality, and nothing else. Yeah. So if we had a Hamiltonian model, then we would have energy conservation as well. Now, many of the conclusions will still follow through for Hamiltonian realizations, but I want to study things in the minimally structured setting first. So what do we get? Well, if we just have a circuit model and we're picking our gates at random, then we don't even have time translation invariance. And so you might expect that there's no energy conservation. And if there's not, if this is minimally structured dynamics, there's no energy conservation, you might expect that we would get thermalization. What does thermalization mean? Systems only ever thermalize to a symmetry sector. What you might think this means is you pick a symmetry sector by charge and dipole, and you pick an initial state with a certain charge and dipole moment. And you might think that you would thermalize with respect to the symmetry sector, meaning that you would explore all of the states in that symmetry sector, and the long time average might look something like equipartition over all of the states in a symmetry sector. And what's shown in these two plots on the left is the charge distribution for that sort of equipartition over a symmetry sector. And you can see the charge distribution looks pretty uniform. And what's shown on the right is what you get numerically if you start with the charge sitting on a single site and then time. And what you see for this circuit model that I gave you is that it looks very non-uniform. Yeah? The charge seems like it stays close to where you started off. And in fact, in the simple circuit model I gave you, you can pick almost any state from Hilbert space, and it looks like you got localization. Yeah, ergodicity is broken for almost any initial condition, and that's really weird because we've not got any energy conservation. And how can you get localization without energy conservation? If you fiddle with a model and you allow longer range gates, then typical initial conditions do in fact thermalize, but there's still a subspace that's exponentially large in system size, which exhibits ergodicity breaking and localization, and this cannot be conventional localization because there's no energy conservation. Yeah. So what is it? Well, the answer to that emerged in this paper over here, and also in simultaneous work by the Munich group, and I'll tell you about that now. And it's simplest to sort of explain by pictures. Yeah. So we're considering quantum dynamics, which conserves charge and dipole moment and has spatial locality. So the dynamics is generated locally in space on some length scale m. And let's say we have some dynamics where there's some state of locally maximal positive charge, which I'll call plus, and some other state of locally maximal negative charge, which I'll call minus. And so now let's consider some state which alternates between regions which are all plus and regions which are all minus, with the domain walls between all plus and all minus regions at least a distance m apart. Yeah? And now let's consider quantum dynamics on this state, generate and just arbitrary quantum dynamics constrained to conserve charge, dipole, and spatial locality. So we come in and we act with our gates, and every such gate acts across either 0 or 1 domain walls by construction. You can't act across 2 domain walls because the domain walls are further apart than the size of the gates. Yeah. If you act across 0 domain walls, then you act on a region that's locally extremal charge, and there's nothing you can do to that consistent with charge conservation. If you act across 1 domain wall, then you act on a region that's locally extremal dipole given the charge. And again, there's nothing you can do to that consistent with dipole conservation. Yeah? I mean, the things you could do consistent with charge conservation are you could delete plus and minus charges in pairs, or you could shuffle them around, but either of those things will change the dipole moment, so it's not allowed. So any such state must be an exact eigenstate of any quantum dynamics, as long as that quantum dynamics conserves charge and dipole and is locally generated. And how many such states are there? Well, it's easy to get a lower bound. You can carve up your system into blocks of size n, and each such block you can allow to be either all plus or all minus. And that gives you at least 2 to the L over m such states, which are product states in the computational basis, but also are exact eigenstates of any quantum dynamics that conserves charge, dipole, and is locally generated. Yeah? And this is an exact, rigorous statement. And now I should say that this is just a lower bound. This is not tight. You can get an exact count by doing transfer matrix, but this is sufficient to make the point that for any charge and dipole conserving locally generated quantum dynamics, there must be a subspace that is exponentially large in system size, within which the dynamics is exactly localized. In fact, there's no dynamics whatsoever. So what does this mean for the time evolution? Well, our time evolution is always generated by some unitary matrix, and the unitary matrix always block diagonalizes by symmetry sector. And in ergodic systems, that's it. Each symmetry block is a random matrix in the appropriate symmetry class. But what happens over here? Well, it can't be a single block. Instead, what you get is that within each symmetry block, you get a further massive block diagonalization. And there's all of these exponentially many 1-by-1 subblocks, and those are the exact eigenstates. But there's also blocks of size 2, 3, 4, 10, and some blocks with size that diverges in the thermodynamic limit. Yeah? So this is the phenomenon that we call Hilbert space shattering, and the Munich group called Hilbert space fragmentation. And if you start within a single subblock, you stay within that subblock forever and ever. You don't explore states in different subblocks, even if they're in the same symmetry sector. So that is the sense in which ergodicity is rigorously broken. Now, this construction generalizes straightforwardly to higher dimensions. So let's say we're in d space dimensions and we conserve charge and also all d components of dipole moment. So the simplest thing you can do is you can just make stripes, and that straightforwardly gives you a number of eigenstates, which is exponential in linear system size. But you can go further than that. You can actually allow the stripes to roughen, as is shown in this plot number C. And now you can make the argument I made first in the x direction and the y direction, and you can rapidly convince yourself that every such roughened stripe eigenstate must also be an eigenstate of the dynamics, of any quantum dynamics that conserves charge, all components of dipole, and is locally generated. And this gives you a number of such states, which is exponential in system area in 2 dimensions. And the argument generalizes to arbitrary dimensions. It just proceeds by dimensional reduction. And in d space dimensions, if you conserve charge and all d components of dipole, and the dynamics is locally generated, then you have a localized subspace, which provably has dimension that's exponential in system volume. Yeah. and you can get still richer structure of frozen states, as shown in panel D, if you have higher multiple moment conservation. Okay, so now this is what you get if you have charge and dipole conservation. How can you actually realize this? Well, the simplest possible realization, which Monica also talked about, is ultra-cold atoms in a tilted potential. So if you have a strong potential tilt, then the center of mass couples to the tilted potential, and you get center of mass conservation up to some free thermal timescale, and center of mass is like dipole, and you should get this sort of fragmentation. And indeed, this has been observed both by the Munich group and the Hangzhou group. We also proposed a realization in atomic clocks, and actually, as I was listening to Monica's talk, I realized that this realization we proposed in atomic clocks is very similar to what Monica was talking about for the resonant fragmentation when 2 delta is U. So maybe I should actually even move this atomic clock thing from proposed to observed. But the point is that this all seems very Baroque, but you can actually see this in cold atoms, and people have already seen this in cold atoms. Yeah? And there may be still other realizations that we haven't figured out yet. Okay, so to summarize the first part of my talk, thinking about these Fracton type conservation laws, where you have conservation laws on multiple moments of charge, it gives very rich behavior. If you have Z2 type conservation laws, as in the exactly solvable lattice models, then you get glassy dynamics, but you do not break ergodicity. But if you promote to U1 conservation laws, then you get truly rich behavior, and you get sort of provable localization in a subspace that's exponentially large in system volume in any dimension, and sort of provable ergodicity breaking, robust ergodicity breaking, with just finitely many conservation laws. And this does not require disorder, and in fact, it's even robust to temporal noise. So you don't even need energy conservation. But what you do need is that this charge and dipole conservation has to be strictly imposed, and the locality also needs to be strict. You need sort of truly local dynamics. And it can be realized in a pre-thermal sense in various experimental platforms. Okay, let me move on. So far I was talking about essentially, you have this breakup of Hilbert space into some small subblocks and some big subblocks. And so far I was talking about these small subblocks, which have this localized dynamics. But now let's talk about the big subblocks. Yeah? And what happens in the big subblocks? And something we showed in this work, which I guess just appeared in World Scientific, is that the dynamics within these big subblocks is actually thermal, or expected generic for minimally structured dynamics to be thermal with respect to a subsector. Yeah? So this is not thermal in the conventional sense. It's not thermal with respect to a symmetry sector. Instead, it's thermal with respect to a subsector. Well, I should qualify. So you have different subsectors, yeah? And some of these subblocks are integrable. So the integrable subblocks are not thermal, but there's also non-integrable subblocks. And in the non-integrable subblocks, you expect the dynamics to be thermal with respect to the subblock. And then you can ask, what does the approach to thermal equilibrium look like? Where I remind again that we're defining thermal equilibrium now with respect to subblocks instead of with respect to symmetry sectors. Now, the standard theory for approach to equilibrium is hydrodynamics. So if you have some system with conserved charges, you might think that the approach to equilibrium, and you have some system with conserved charges and it equilibrates, you might think that the equilibration would be governed by hydrodynamics. And the canonical long-time behavior is diffusion, which is governed by the diffusion equation, which is shown over here. And the diffusion equation has this characteristic relationship between length scales and time scales, where length scales go like square root of time. But in these fractonic settings, the approach to equilibrium is still given by hydrodynamics, but it's not standard hydrodynamics. And in particular, it's not diffusion. Instead, you get hydrodynamics in some unusual universality class. In fact, depending on which multiple moments you impose, there's infinitely many possible non-standard universality classes. And all of these non-standard universality classes exhibit subdiffusion, meaning that things relax slower than diffusion. So we worked this out in this paper from a year ago. Let me give you a quick rundown of the argument. So the elementary mobile excitations, remember, are dipoles. Single charges cannot move. And if you put a dipole in a uniform field, it doesn't respond. Yeah, dipoles feel no force in uniform field. So that tells us that the conductivity should be 0. And if the system thermalizes, then I have an Einstein relation. And if the conductivity is 0, then the diffusion constant must also be 0. So the approach to equilibrium must be slower than diffusion. Yeah. the mobile objects are dipoles, and dipoles are vector objects. And so the basic current here should be a two-index object, Gij, dipole in direction I, moving in direction j. And that should have some continuity equation, which looks something like this. And you can derive this from Keldysh and sort of doing Schwinger-Keldysh contour integrals, but you don't have to. You can basically just guess where it has to be. It's from continuity. And now the question becomes, well, how is Gij related to gradients of the charge density? Yeah. So again, you can get that from Schwinger-Keldysh, but you can also get it from standard thermodynamic arguments. And what thermodynamic arguments tell you essentially is that Gij, the dipole current, is related to two derivatives of the chemical potential, or two derivatives of the charge density. Yeah. So altogether, the continuity equation involves the square of the Laplacian. Or in general, if you conserve the first n multiple moments, then you get a modified diffusion equation, which looks like what we wrote down here. So n is 0 is only charge conservation. That gives you back the ordinary diffusion equation. N is 1 is charge and dipole. So you replace the Laplacian in the diffusion equation by square of the Laplacian. N is 2 would be charge dipole quadrupole. Then you have cube of the Laplacian and so forth. And obviously, n can be any whole number. So you have infinitely many possible universality classes of generalized subdiffusion equation for Fracton hydrodynamics. And each of these exhibits subdiffusion, where the relationship between length scales and time scales is non-standard. Length scale goes like time scale to some power smaller than it would be for ordinary diffusion. So there's this infinite family of subdiffusive hydrodynamic universality classes. Can you realize this? Well, yes, you can. So Wasim Bakr's group looked at cold atoms in a very small tilt potential. So if you have a small tilt, then you also get emergent dipole conservation, but only on long length scales. Yeah? But long length scales is fine because hydrodynamics is a theory of long length scales. So you might expect that the long wavelength, long time behavior would be governed by hydrodynamics. And in fact, the Bakr group observed subdiffusion, and that subdiffusion has a very clean interpretation in terms of the sort of long wavelength behavior of their system is governed by this non-standard universality class that we derived for Fracton hydrodynamics. There's also another potential realization, which was proposed back in 2007 by Subir's group without reference to fractons, which can also be understood very cleanly in terms of Fracton hydrodynamics. And there may be other realizations as well that we haven't identified yet. Maybe now let me tell you about one cute bit of physics that we realized fairly recently. And that is that this Fracton hydrodynamics that I've been talking about, these sort of non-standard hydrodynamic universality classes with multiple conservation, they have some hidden, what we call quasi-conservation laws that are not sort of put in my hand. Yeah. So the only things that the only conservation laws that we explicitly put in are charge and dipole conservation. And we get this modified hydrodynamics with square of the Laplacian. But in fact, at the level of linear hydrodynamics, you find that every harmonic function charge is conserved. So what do I mean by a harmonic function charge? Well, pick any harmonic function f. By a harmonic function, I mean that Laplacian of f is 0. Yeah. So pick any harmonic function f and integrate it against the charge density, and that defines a corresponding charge. And for every harmonic function, the corresponding charge is conserved at the level of linear hydrodynamics, both in infinite space and in a finite domain with charge and dipole conserving boundary conditions. Yeah? And that's an exact statement to the level of linear hydrodynamics. And in dimensions bigger than 1, that means that there's infinitely many apparent conservation laws. Yeah. So is this like MBL after all? I mean, have we got infinitely many emergent conservation laws? Well, not quite, because these conservation laws are only there at the level of linear hydrodynamics. Yeah? Once you put in corrections to linear hydrodynamics, which could be either non-linear sort of fluctuation corrections to hydrodynamics or lattice anisotropies, then these conservation laws go away. They're accidental. Yeah? They're not truly there in the hydrodynamics. They're there in the linear hydrodynamics, but they're broken by nonlinear corrections, and they're broken by lattice anisotropies. But these corrections that break these conservation laws, those are generally irrelevant corrections. Yeah? So if you look at the relaxation of these conservation laws, what you have is, they do relax, they're not truly conserved, yeah? But they relax via dangerously irrelevant perturbations, yeah? Which means that you get relaxation with characteristic exponents that are different from what naive power counting would predict. So the Fracton hydrodynamics gives some naive power counting, which is slower than diffusion. But in fact, if you look at the right initial condition, it can relax even more slowly than that naive power counting would predict, because the relaxation actually depends on some dangerously irrelevant corrections to linear hydrodynamics. Yeah? So that's all explained in detail in this paper over here, which we put in archive about a month ago. Okay, so can we explore any of this numerically?
Well, it's 5 minutes.
Okay, yeah, 5 minutes is plenty. You might think that would be tough because you need very large system sizes to see hydrodynamics, but this is where a new technique comes in, which we call sort of automaton Monte Carlo. So the idea is, let's consider a quantum circuit that maps product states to product states, subject to some constraints. So this is the sort of state analog of Clifford circuits, and Serang's also written some papers with this. So Clifford circuits map product operators to product operators. Like automaton circuits map product states to product states, which means that for product states on the computational basis, they don't generate any entanglement and they're simulable. Yeah? However, if you consider a generic initial condition, the time evolution looks completely indistinguishable from Haar random dynamics. Yeah? It's sort of, it's simulable for a very special class of initial conditions, and for generic initial conditions, it looks indistinguishable from Haar random dynamics. So what do you do? Well, what you do is you consider a generic initial condition, yeah? And then you take the projection onto, let's say, 10 randomly chosen product states on the computational basis. You time evolve those, that can be done efficiently. Yeah? Then you take the projection onto another 10 randomly chosen product states, time evolve those, and average. Yeah? And you just iterate until you get convergence. So there's two ideas here, that there's a special class of initial conditions, which is efficiently simulable. Yeah? And then you can combine this with Monte Carlo techniques, where you can take random projections onto these special initial conditions and time evolve those and iterate until convergence. And this gives us a sort of numerically tractable way of simulating sort of constrained quantum dynamics for actually pretty large system sizes. And you can do this and you can use it to verify the subdiffusive exponents. And in fact, we first saw subdiffusion in this paper over here numerically before we really sort of understood full analytic framework of Fracton hydrodynamics. This is what sort of inspired Fracton hydrodynamics. Okay, so with that, let me summarize part 2. So when fractons thermalize, the approach to equilibrium is described by hydrodynamics in a non-standard universality class. And in fact, there's infinitely many non-standard universality classes, and they all exhibit subdiffusion. And you don't need fractons to realize them. Yeah? You can also realize them in ultra-cold atoms where there's no fractons to be seen. We introduced a new numerical technique capable of exploring this, and it's been observed in one experiment. So just to summarize my whole talk, non-equilibrium many-body systems are terra incognita. We want to find ways to evade equilibration. The previously known ways relied on having infinitely many conservation laws, but actually you can get a lot of mileage with just finitely many conservation laws. In fact, just 2 can suffice if you pick the right 2, and the right 2 is sort of guided by the study of fractons. Fractons are a new class of quantum states of matter, which have excitation with restricted mobility coming about because of conservation laws on multiple moments of charge. If those conservation laws are Z2 type, then you get glassy dynamics, but at the end of the day, you do get ergodicity. But if you promote from Z2 conservation laws to U1 conservation laws, now you get really rich physics. Yeah. So what you get is, well, you have this exponentially large volume of Hilbert space, which has provable and exactly localized dynamics, even without disorder and even without energy conservation, just following from finitely many conservation laws plus spatial locality. You have these infinitely many subdiffusive universality classes, these hidden quasi-conservation laws. So there's this whole wealth of new physics, which we're still exploring. We've also introduced a new numerical tool to explore it, this automaton circuit Monte Carlo technique. And the key phenomena have in fact been observed by 3 different experimental groups. And we're still discovering new things. So this is a wide open frontier. There's lots more to be found. So with that, I'm just about out of time. I'll just thank my collaborators on this project. I should thank in particular my former student, Abhinav Prem, my former postdoc, Mike Prepko, and my collaborators, Vedha Khemani and Andy Lucas, and various other collaborators. And with that, I will conclude.